Good morning, everyone. Welcome to Trevor Hunt's PhD defense. My name is Sigrid Elschot. I've had the privilege of being Trevor's advisor these past years, but before we begin, I would just like to express my gratitude to the committee, Professor Farhak, Professor Harv, Professor Capelli, and Professor Oppenheim, who's joining us on Zoom. So Trevor came to Stanford in 2018 after graduating from the University of Washington, where he earned a BS in Aeroastro.
Correct.
And a minor in applied math. Did I get that right?
Correct, yeah.
Okay.
Almost forgot.
So over the past 6 years at Stanford, Trevor has been a phenomenal student, earning highs in his classes, tackling the very difficult research topic of understanding plasma formation on a meteoroid, which we'll talk about today. He was awarded first place out of 38 submissions at the National Earthsea Student Paper Competition in 2024. He's also been an absolutely incredible TA, teaching graduate dynamics as well as plasma engineering, and he earned the Centennial TA Award for outstanding contributions to teaching. Trevor, this one's hard. You've been an amazing student. I can't thank you enough for the past years, from talking plasma with me, always stepping up, helping out with the younger students in the lab. I'm just so grateful for the past years. So that's what it was.
Thank you so much, Professor Elschot. I'm getting messages from someone online. I'm just going to real quick make sure that, okay, we're good. All right. So thank you all for being here. And thank you again to my committee for being here in person and Professor Meers Oppenheim online. It's very much my honor to have been a student here at Stanford and working in Professor Elschot's lab on the wonderful subject of meteors that are entering Earth's atmosphere, which is a thing that happens every day. And so, yeah, I will talk all about meteors today. So you have billions of these tiny particles that are entering Earth's atmosphere every day. And there's a few different ways that you can observe them. You could use a camera, just point a camera into the sky, perhaps with a fancy mirror tracking system, as is the case in this video. This is a video from Peter Brown's group. Or you can use radar data using very sensitive radar instruments, such as this one right here, which is Hikamarka Radio Observatory. This particular radar image contains 5 different meteors, like 6 different signatures of the meteors. And so these are vast data sets, and we can study those data sets using some advanced tools that are very modern, such as machine learning, and then also computational simulation techniques. So I do want to clarify, we're talking about very tiny meteoroid particles. We're not talking about the bigger ones. So looking at a meteoroid in a microscope, this is what it might look like on the order of micrometers. We're not talking about large asteroids. There has been a large asteroid in the news. The chance that it will hit Earth has gone down to 0. This did not get publicized well. And then spacecraft entering other atmospheres, that it's very much a controlled meteor, a large meteor, very much a related subject. But since we're focusing on the small meteoroids, we're dealing with a rarefied flow regime. And so also very hypersonic flows. And then there's also the why. Why are meteors so important, and why do we care about them, especially the tiny particles? Well, tiny particles probably came from bigger asteroids at some point in time, or during the formation of the early solar system, then all those small particles spread out, and there's many different origins that they can come from. They also, we can, based on the trajectory of the meteor, then you can figure out where did the meteoroid particle come from. You can figure out its trajectory. You can also calculate its mass or density using some advanced techniques. And so scientists care a lot about this, since the small particles would often be neglected otherwise. You can also use these particles as a probe for the upper atmosphere from 80 to 120 kilometers. This is a region of the atmosphere that's very hard to observe using other techniques, so it's very valuable to get information using meteoroid and meteor observations. These particles pose a major risk to spacecraft in the space environment. And with the exponentially growing population of spacecraft, it's very important that we continue to assess the threats that they pose and then figure out, how can we design spacecraft to not have that concern as much, especially electrical damage, where you have an expanding plasma that can emit radio frequency waves that can cause interference. Speaking of exponentially growing populations of spacecraft, that means you're going to have exponentially growing populations of space debris. So eventually a lot of space debris will re-enter Earth's atmosphere, and then it looks like a meteor. And so if we can track that, then we can use all the same techniques. So as I mentioned before, I will be focusing on radar observations of meteors, specifically high power, large aperture radar observations. These produce terabytes of data. Like if you observe for one night, it's a lot of data. It's a long stream of data containing thousands of meteor echoes. And we have to talk a little bit about the shape of the meteor, the anatomy of the meteor. When I say the word meteoroid, I'm referring to a solid particle. It's either not entered Earth's atmosphere yet, or it started to vaporize into a gas, and then it turns into a meteor. Meteor is the thing that's entering Earth's atmosphere and it's vaporized and or become a plasma through ionization. Then the meteor is broken down into two different regions, although they do kind of blend together. There is the meteor head echo, or the meteor head, which then in the radar data, it forms a head echo. That is a very high density region of electrons that reflects these radio waves. And this is an altitude versus time plot. So as this meteor is going down and approaching the facility that is transmitting radio waves, you see this streak. Then there's also the meteor trail, which as that plasma that's following the meteoroid eventually undergoes collisions with the background atmosphere at hypersonic velocities, then it will very quickly slow down and equilibrate with respect to the background atmosphere. And then it forms this trail behind it that then will start diffusing, and eventually the ions and electrons will recombine, and then the plasma disappears over a period of time. You can observe what's called a non-specular trail echo, or a range spread trail echo in the radar data. This occurs when you have an alignment between the radar's beam 90 degrees to the background magnetic field. And this is because the meteor trail plasma tends to align itself with the magnetic field such that something called Bragg scattering occurs. And that is it's kind of a mechanism through constructive interference where you get much brighter coherent reflections that then show up in the data very prominently when you have this 90-degree alignment. You can also observe specular trail echoes when you have a different 90-degree alignment, this time between the radar beam and the meteor trail. The reason why in this data we see both at once, we think is just because it's two different meteors. As I mentioned, you often see a lot of meteors in these data sets, so they might not be the same event. However, they might be if there's a few reasons why it could be. But my research focuses primarily on the head echoes and the non-specular trail echoes because those are the ones that you need the higher power radar instruments to observe. Specular trail echoes have been studied a lot more because you can use lower power radars to observe them. So a bit more of a mature field. I'm interested in the researchy subject with these other signatures. So anytime that we're doing research, and really especially when we're doing research with plasmas, we have to think of research as being broken into kind of three main pillars. But they are not just independently existing pillars, they're very interconnected. You have your theory where you're figuring out closed-formed equations based on your physics and you're trying to solve them analytically, or maybe a little bit numerically. But then with computation, you are solving high-dimensional systems computationally on large distributed networks of computers and compute cores, maybe supercomputers. And so it's usually discretized calculations that are solved computationally. Then, of course, you have your experiment where you're observing meteors in real life using radars for this work. And my research focuses primarily on the experiment and the computation because there's a lot of wonderful theory that already exists that we want to kind of reference back to. One thing I want to point out is that a radar, it observes in particular the brightness of a meteor, as well as its trajectory and some other things. But the brightness, or the signal to noise ratio, is the technical radar term for that. That every radar will have signal to noise ratio of its observation. So it's very easy to quantify. From that, with some parameters, you can then get the radar cross-section of a meteor, but you can't just get mass or density of the meteoroid on its own. You then need some sort of computational technique that models the meteor and the meteoroid to then figure out the mass loss rate and therefore the mass or the density through other techniques. Everything references back to the theory, though. So you can use theory to try to interpret mass and density or computation. And of course, the computation also references back to theory. We look for agreement between those two methods. So I will talk about how this shows up in the actual meteor literature. So Professor Sigrid Elschot did her own PhD on meteors, and she initially just assumed that the meteor head plasma that is responsible for the head echo is a sphere with a Gaussian electron density with some radius, some peak density. Fantastic theory. And then basically her theory figures out, based on how much transmitted power and then the properties of this meteoroid and its plasma, then how much energy is reflected back to the radar. On its own, that is very valuable for interpreting radar measurements. But then, of course, assuming it's a sphere is a rather significant assumption. And so Dumont and Oppenheim in 2017 published their work on using a physical gas dynamics model to more accurately resolve the plasma shape, where obviously it's undergoing collisions at hypersonic velocities, so you don't expect it to be spherically symmetric. That has been verified using a computational particle and cell plasma simulation. And the simulation allows you to relax a lot of assumptions that the theory makes just because of the nature of discretizing the computations and resolving more of the physics. But what's very cool is that they're very similar. That it basically validates the existing analytical theory for the meteor head echo plasma. So this is very cool. And then you don't just need to know the shape of the plasma in order to figure out the rate, understand signal noise ratio of the radar observations and how that correlates with the mass and properties. You then need to do something to understand how, based on how many or how much power is transmitted and reflects from that plasma, how much will be detected by the radar. And for that, we use computational finite difference time domain simulation of the radio wave scattering process. Now moving from meteor head echoes to meteor trails. Trails, as I mentioned, are caused by plasma instabilities that lead to turbulence that aligns itself with the background magnetic field. Linear theories using plasma fluid equations and kinetic theory equations can be used to figure out the altitude range at which trails tend to occur. And we do see in the experimental data that trails tend to occur generally starting at around 95 kilometers, but mostly going up to like 100 and 105 is a little bit more common. That's where most trails are observed. And so theory demonstrates that that makes sense based on the fundamental physics of the plasmas and how they tend to reflect more. Trails have also been simulated using particle and cell simulation, and especially the growth of instabilities leading to turbulence. And this is in the reference frame of the background atmosphere. The plasma simulation of the head echo is in the reference frame of the head or the meteoroid traveling with the head echo itself. So there's two different ways you can simulate meteor plasmas, and I will touch on both. Now moving on to experimental research, and I'm doing this after the theory for the reason that for Professor Sigrid Elschot's PhD, she used the Altair radar, which is a very sensitive radar in the middle of the Pacific Ocean, to observe meteors, and then used her theory to then quantify the mass of those meteors at Altair. Then she went on to also quantify the density by now, instead of just using the signal to noise ratio, also using the deceleration that the radar can measure. Then she also looked at trails at Altair. So 3 publications on Altair. Altair is very clearly a very capable facility. There's one problem. It is a little bit more on the military side as far as the facility is concerned. It is funded by the DoD. And so what that means is it can be challenging to obtain data there without it going through a rigorous declassification process. And so what we actually want to do is also figure out how can we observe meteors at other facilities, especially ones that might be funded by the National Science Foundation. And so the head echo populations, like just all of the properties of all of the meteor head echoes that are observed at 3 other non-Altair facilities funded by the NSF, has been done and got some very cool results. And then you can then quantify the mass at some facilities, similarly using the physical gas dynamics model and then finite difference time domain simulation. This has all been done before. Now, where do I come in with my PhD? Well, I said, I think we can improve upon the prior studies and investigations comparing different facilities, especially the non-Altair facilities, and more accurately quantify the meteoroid trajectories and decelerations and mass and density eventually, also the atmospheric neutral density based on the decelerations, using radar measurements at other facilities. And then secondly, I wanted to develop efficient machine learning techniques that can rapidly identify thousands of meteors in these radar data sets for further processing and greatly increasing the efficiency of our science that we can do. Then I said, let's enhance our computational tools to then better understand the properties of meteoroids, including the mass and density eventually, and just in general understanding the physics better, and also understanding how do the trails form and then get observed. And so going back to the first goal, what I did is I performed the first analysis of concurrent observations, so simultaneous observations at 3 different radar facilities around the world. That eliminates a bunch of observation biases, and I leveraged the Doppler shift in a way that has not really been done too much before outside of Altair to get the most accurate measurements of meteoroid deceleration. Then I developed a model to generate synthetic meteor head echoes. essentially that means I'm generating fake head echoes in essentially fake radar data. But the idea behind that is you can then train a machine learning algorithm, such as a neural network, to detect real meteor echoes in real data without meticulously having to label a bunch of head echoes in your data. And so that increases efficiency of identifying meteors by an order of magnitude. And then I use particle and cell plasma simulation to investigate the possible effects of meteoroids not ablating isotropically. It has been assumed very frequently in the theory, including the theories I mentioned, that meteoroid particles are basically spherical and ablate equally, uniformly in every direction. But I then investigated, what if that's not the case? What does that look like? And how does that change the observed radar cross-section and signal-to-noise ratio of the meteor? Then I performed the world's first plasma simulations that resolve both the meteor head echo, or the head echo plasma, and then the trail echo plasma in the same computational domain in the reference frame of the meteoroid. And so that all of this I'm very excited to share with you today. So now moving on to radar data. So what exactly is a high power large aperture radar observing? Well, it collects raw in-phase and quadrature data. What those words mean essentially is just a long stream of complex numbers in time. A radar transmits radio waves into the atmosphere at some carrier frequency, and then it listens for the waves that it transmitted for some time for those waves to go at the speed of light and bounce off of other plasmas in the ionosphere or meteors. And ultimately, it's going to receive radio waves with some amplitude and phase, which is encoded in the complex stream of numbers. So talking specifically about how meteor head echoes are observed by radars. These radars tend to have very thin beams, and then when a meteoroid, well, initially it's transmitting pulses every 1 to 2 milliseconds, so it's constantly pulsing like that, then waiting for reception in between pulses. As the meteoroid goes through the beam, then the head echo plasma will immediately surround the meteoroid with very high plasma density. That's going to reflect radio waves on subsequent pulses. And then from that, the meteoroid will have some velocity, but then there'll be some component of velocity in the direction of the beam. And the radio waves are going to be shifted up in frequency due to a Doppler shift that occurs. And that Doppler shift can be measured by the radar quite easily to resolve the meteoroid's velocity in that direction. You can also quantify transverse velocity using a technique called interferometry. I won't discuss that too much in this presentation, but it's very useful at facilities such as Hikamarka. Then you can arrange the data in such a way where you have altitude on the y-axis and time on the x-axis. But what you'll notice is that this pulse is a finite length. And so over the speed of light, it's going to spread out over altitude. And so what we do is we phase code the pulse. And then effectively, we can just convolve the received data with that phase-coded pulse. We do have to account for the Doppler shift. But what happens when we decode the data using something like a matched filter is you get this very nice streak over altitude and time. That is the meteor head echo that we can then pull out of our data and use to do our science and then quantify properties. So then we'll draw a region surrounding the meteor head echo streak and then pull out the complex data. At every point in time, we're going to pick the point with maximum signal to noise ratio, pull out that complex data, go along the whole streak. Then you have a long string of complex numbers. And then what you can do is by taking the phase difference between all of those points, that relates very closely to the Doppler shift. There is aliasing that happens because you can only measure angles to 2 pi radians. And so luckily there is a technique that had been applied before at Altair to remove that modulo and then get a very accurate range rate or radial velocity profile. And then you can very easily see the deceleration from 45 kilometers per second to 43.5 in this case. This is the accuracy increase that I was able to then take from Altair and then implement at the other 3 facilities that then allows me to get the results that I'm about to show you. First of all, let's talk a little bit more about the 3 facilities that I used. So there's Riser N, which is in Nunavut, Canada. It's an AMISER facility, and it's very capable. Then there's the Millstone Hill facility in Massachusetts, and then Hikamarka Radio Observatory, also very capable. All of them are very capable but Hikamarka is in Lima, Peru. And they all operate their own way. They have little quirks. Hikamarka operates at a lower carrier frequency. It's at VHF rather than UHF. That means very high frequency versus ultra high frequency. I mean, it's kind of on the lower end of frequencies that would be used to detect plasmas in the atmosphere and the ionosphere. And so lower frequency radars detect less dense plasmas. Hikamarka therefore sees the most meteors. However, it also sees the most other phenomena that form plasmas in the ionosphere. So its data will be the most complex. Millstone Hill, we did not just point the beam straight overhead. The beam was pointed at a 45-degree elevation angle. And that does affect the radial velocity measurements because meteors are always coming down from the sky towards the ground. That does influence our data. We did this because of interference that occurred when that radar was pointed straight up at the time. That's since been resolved, so we could repeat that experiment, but I will show you the results. So at Riser N and Hikamarka, I analyzed 400 meteors at all three of the facilities. But what I want to point out is that Riser and Hikamarka, we see this obvious trend. And here I have altitude on the y-axis, radial velocity on the x-axis, altitude on the y-axis, and then the color of each point is the deceleration of the meteoroid. So it's acceleration, but positive is slowing down. And what we see is that for these meteoroids that are over a radial velocity of 40 kilometers per second at both of these facilities, there's a very clear trend between the deceleration being higher at the lower altitudes. That means that's because the density of the neutral atmosphere is much higher at those lower altitudes. And so these meteoroids are slowing down more. Therefore, we could select all of those meteors or meteoroids and put them into an algorithm, some sort of optimization algorithm to determine the atmospheric density profile. So that is a subject for future work. But then with the beam at 45 degrees at Millstone, unfortunately, this trend does go away. So you need the beam at 90 degrees. We also can identify a bunch of other quirks in how each radar identifies these meteors. And so that was part of the value of doing this concurrent data collect, where we're eliminating any biases due to differences in the meteor population throughout the year or differences due to variation in the atmosphere globally that tends to occur when space weather changes. There's a major limitation to this whole analysis so far, and that is the number n of meteors that are being observed and processed. Finding 400 meteor head echoes is a very slow process manually. You have to really look for the meteors, and then some of them you have to throw out. Hikamarka observed thousands of meteors, so we can do much better. And so I thought, okay, it wouldn't be great if we had some non-trivial algorithm that could identify meteor head echoes in the data, especially considering these are some examples of head echoes, these three on the left, and then this one on the right, that's a satellite. That is not a head echo, but it looks a lot like one, like a long duration head echo. And so to the untrained eye, they might identify this. And so in this case, there's some interference. In this case, there's some non-specular trail echoes that are sort of interfering with the head echo. In this case, you have the equatorial electrojet, which is something that you either see at Hikamarka or you don't at any given time. But if the equatorial electrojet is there, it's a plasma that tends to occur at the equator and it flows, then it can really interfere with the head echoes, and you can't just look for signals above a certain signal strength. So no trivial algorithm to detect head echoes. You have to meticulously go through with the human eye. Let's do machine learning. And so prior work has been done into machine learning to detect meteor head echoes, mostly by one PhD student at Penn State, Felix Lee. He's a very nice guy, but kind of where I thought maybe we could take his work and then really improve, or, well, his work is fantastic, but then where we could really make the work very readily applicable is we could remove the need for the manual labeling of tens of thousands of radar images containing meteors at any given facility that you want to implement these techniques on. And so that's where I said, let's generate physics-driven synthetic data to then train these neural networks. And so to do so, we have to make some assumptions about these meteors and their head echoes. We initially assume that their range or their distance from the radar facility just decreases via an exponential. And so that's because the atmospheric density is increasing as an exponential, and there is meteor deceleration, but it's not that much compared to the overall velocity during the time you're observing it. And so you can just model it as an exponential. We pick the initial range, velocity, and deceleration within kind of parameters that we would expect from prior data, the populations of 400 that I observed before. And then the received complex voltage signal, so this is the complex number that the radars are observing, will depend on all of the relevant physics. So the first one is the overall signal strength of your meteor, the signal to noise ratio, which is a function of how big the meteoroid is and how quickly it's losing its mass. You'll see the pulse code that you transmitted. That just gets reflected. But then there's also a Doppler shift that shows up because it's moving very quickly, which then, as I mentioned, shows up as a phase difference over time. And then you also have to include the variation in signal strength due to the motion through the radar beam. It will be weak when the meteor is at the edge and then strong when the meteor is close to the center. That can be approximately modeled using a sinc function, or the main lobe of the sinc function. So we use that formula, but we have to recognize that meteor head echoes don't just exist on their own in the data. It's not just like you have a head echo and then it's zero everywhere else. In practice, there's going to be some sort of other plasma phenomena that are occurring in the ionosphere. You're always going to have noise as well in your data. Every radar observes noise. And so we have to combine these examples of synthetic head echoes with some sort of examples of noise. We could figure out a way to generate the noise or the equatorial electrojet or other background phenomena synthetically, but it's actually not that hard to identify real examples in our data pretty quickly within a few hours, because there's many more examples of that than there are meteor head echoes. And so that's a much faster process. We can then create our segments that we use to train our neural network by combining the two, the synthetic head echo with the real background phenomena additively. And then this is raw data. Again, we have the altitude aliasing, but if we decode this, you can very clearly see the meteor streak. But we're going to train the neural network on raw data because that's actually much faster and it still gets very accurate results. We take the training segment with both signatures. We give that a label of 1, contains a head echo. We also pass just the example of background phenomena with a label of 0 into our training loop. That allows the neural network to discriminate between examples containing a head echo and examples not containing a head echo. And what I did is I implemented a very standard machine learning architecture, a convolutional neural network with 3 layers based on ResNet. We use as input the raw radar data, just complex raw data, no pre-processing, and we're trusting the neural network to learn the features of the pulse code which are in the synthetic data that we're generating very rapidly. And so then we have 3 convolutional layers, and then the output is just the probability that you have a head echo that the neural network thinks. If that's greater than 0.5, then we say this contains a head echo. And so what I did is I created contour plots showing the training process of each, of 2 different particular real head echoes. These are real head echoes. These are not synthetic head echoes, but the neural network is actively being trained on synthetic data. And as we train the neural network, it just immediately focuses in on the head echo. It ignores the trail. Sorry, there's usually a way to optimize and make this better quality, but there we go, optimize for video sharing. So I'm going to show this one more time for those on Zoom if I can, but yeah, so initially you see the noise and then it quickly zooms in on the head echo. At Hikamarka, here's an example with a non-specular trail that occurs immediately after. And so in that case, it's initially detecting the trail, but it very quickly, as the neural network is training, it focuses on the head echo. It says that is important for making my decision that this contains a head echo. We're going to ignore the trail because we want to detect the meteor head echo. That is what we are training for. So it identifies head echoes and rejects everything else. Good. That's what we want. We're solving the right problem. Now, we have to quantify the performance of this neural network more rigorously than just, oh, it's detecting the right thing. And so I meticulously went through 4 test sets at 3 different facilities, the same 3 facilities, but at Hikamarka, I split it into 2 test sets. Examples where there is no equatorial electrojet, which I mentioned is kind of one of the strongest signals that would interfere with meteor head echoes. And then a case where there are examples with the equatorial electrojet. And so then using the human eye, but a very trained human eye, because I've been going through this data for a long time, I looked for even the weakest head echoes that exist in these test sets, and I manually labeled, and I compared that with what our neural network is determining. Overall, I got an agreement or an accuracy above 99% at Riser N and Millstone. Those 2 facilities tend to observe fewer examples of other phenomena besides meteors in that altitude range. But then Hikamarka observes kind of more of those other signals. And so we get 96, 97% approximately, but still very accurate overall. Then sensitivity, this is a metric of all of the meteor head echoes that are in these test sets, how many of them are we catching with our algorithm? This is above 70% everywhere. And this is very good, even though we're missing 30%, those 30% they tend to be very weak head echoes. And ultimately, it's catching all of the head echoes that the human eye would catch, and then probably more, unless you're very meticulously looking through the data and therefore spending a lot of time looking for these head echoes. So overall, this is the algorithm you want to use if you want to get a mostly comprehensive data set containing all of your head or containing most of your head echoes at a given facility. And you can train this quickly just using the synthetic model for a new facility. So with many thousands of head echoes that we can quickly identify using this technique, after turning on our radar and getting data and then quickly selecting all of those examples of background phenomena, we want to best understand what all of these radars are actually seeing. And so again, going back to the computational methods to try to better quantify the properties of these meteors, we do know, just based on intuition, that higher signal-to-noise ratio meteors are heavier or losing mass more quickly. So a lot of work in the past has gone into understanding that precise relationship between radar measurements and how big are these particles actually. Then there's the fact that meteoroids that are decelerating slower tend to be larger because they have more inertia. So again, that goes back to the atmospheric density over altitude and the decelerations. And what we use to unite theory or computation and experiment is the radar equation. This gets you the radar cross-section of a meteor observed in experimental data, and also based on a meteoroid's properties using our theory or computational models, we can predict the radar cross-section using a chain of tools. And so left-hand side here is experiment. There's a lot of parameters here, and I know they're not defined, but that's because there's a lot of them. They're really just specific to any given radar. I do have an extra slide defining them all, but ultimately you can solve for all of these quantities. And then you have the signal-noise ratio, which is, again, the brightness of the meteor observed by the radar. We equate this radar cross-section measured experimentally to a function we determined using our computational models based on the properties of the meteoroid. Properties of the meteoroid are all interconnected a little bit, and so that's the job of the model, is to kind of pull apart those dependencies. So now what simulation tools do you need to resolve the radar cross-section, which then we can use to inform our radar measurements using, say, a lookup table of radar cross-sections and the other measured quantities such as altitude and velocity deceleration. Well, initially, what you want to understand is, how is this meteoroid ablating? Like, how does this material turn from a solid into a gas and vaporize? What are the velocities of those gas particles coming off of the meteoroid? Then it'll ionize and turn into a plasma. So we need some sort of plasma model, some plasma. And for computational tools, we'd use particle and cell simulation. A lot of my work has focused on this part right here, using particle and cell plasma simulation to resolve the plasma shape. Then you pass those results into a finite difference time domain scattering simulation that I mentioned earlier. I'm doing an ongoing collaboration with Alex Green and Meers Oppenheim's group to perform those simulations based on my plasma results. Then you get radar cross-section out of that, and then you use that to analyze your radar observations. Using existing simulations of the meteoroid ablation, and I collaborated with Joseph Ferguson on a heat and mass transfer solver of the meteoroid. And what we found is that meteoroids very much might not be ablating isotropically or equally uniformly in every direction. And so the novel concept here is now using those results to inform meteor plasma formation using the particle and cell simulations. And so we're going to go ahead and do this. Simulation results using the heat and mass transfer solver show that meteoroids on the size scales that are observed by these radars very much might not be isothermal. They might have like 100 or 200 Kelvin difference from the front side facing the hypersonic atmosphere in a rarefied regime to the backside where they're quite a bit cooler. This greatly affects the mass loss rate. And so ablation is clearly not isotropic, or at least it might not be, but depending on realistic sizes of the meteoroids. And this raised a lot of questions about the existing analytical theories. And so now, how are we going to assess this effect using our plasma particle and cell simulation? This is a code that was developed in Meers Oppenheim's group, but I extended it. I implemented a bunch of subroutines to kind of make all of this research work smoothly. And this is a three-dimensional Cartesian uniform grid code, and it's electrostatic. So we're assuming that the meteor plasma itself does not induce a large magnetic field in and of itself, but there is a background magnetic field. Particle and cell codes, what they do is they calculate particle positions moving. They're like point particles moving in three-dimensional space. But then every time step, it'll take all of the particles in your domain and figure out the densities of both ions and electrons and then neutral particles on a grid. And then with those particle densities, then you figure out the electrostatic potential field using Poisson's equation, then use that to calculate the electric field at every particle's position. And then you can advance the velocity and position of every single particle in your simulation, account for collisions between those particles in the hypersonic atmosphere using the Monte Carlo collision method, then this loop happens on every single time step. And so how we configure our plasma simulation domain to observe meteors, this is a three-dimensional domain, and we need some boundary conditions. So we're going to have the atmosphere is flowing from left to right. It's flowing in at the left boundary, out at the right boundary in this figure here. And it's at an altitude of 100 kilometers with appropriate neutral density, and then a velocity of 40 kilometers per second. And then, so you have inflow, outflow as your boundary conditions. All of the other boundaries that are transverse to the meteor's direction of motion are periodic. This allows the field solve to be 10 times faster approximately, but it does assume a two-dimensional infinite array of meteors is entering in parallel. The trick in that case is to consider that the boundaries should be positioned far enough away that each adjacent meteor does not interfere much with each other. Then you're generating particles at a certain rate at the middle of the domain. That is your meteoroid, or not necessarily at the middle, but it's some constant generation of these vaporizing particles. And then on every time step, there is the odds determined by the Monte Carlo collision method that these particles will collide with background atmospheric particles moving at 40 kilometers per second. And then from there, then there's also the particle that you'll have an ionizing collision where a neutral particle becomes an ion and an electron. That's how you get your plasma, the plasma shape that you see in the domain. And so then how do we then plug in the results from those ablation solvers to the particle and cell simulation? We're going to compare the two cases of isotropic ablation and then preferentially frontal ablation, where most of the mass is ablated from the front side. And we assume that the mass loss rate in the preferentially frontal case is determined proportional to the cosine angle of a point on the surface and the oncoming atmosphere. And then you assume that no mass is lost from the back side. However, once you determine using our probability distribution where a particle will be ablated, then you initialize it with a half Maxwellian. And so what this effectively means is that in the isotropic ablation case, if we look at the neutral density in our simulation domain after some time, isotropic ablation, you get circles with some shift downstream due to collisions. Preferentially frontal ablation, you see this cusp forming where many fewer particles are ejected backwards. Some still are because you have particles that start on the side of the meteoroid and then are kicked backwards or downstream, but then most go upstream in that case. That then begs the question, how does that affect the plasma density distribution surrounding the meteoroid? Surprisingly, the shapes look very similar. It's these two cases right here. Can't really see any differences visually, so we have to compare the percent differences. On the left, we also have the physical gas dynamics model that I mentioned earlier, the de Oppenheim model. So we compare all of these things, but visually it's very similar from the two simulation cases. Model matches the isotropic ablation case very well. This model does not resolve the far region in upstream. And so that's why the difference diverges there. But in the center of the domain, we see very good agreement. For the case with preferentially frontal ablation, we do start to see a difference in that interior region of up to about 70%. But overall, the shape looks very similar. If we compare the difference between the isotropic and preferentially frontal ablation cases from the simulation, we do also see that 70% difference. So we have that difference. In future work, we will quantify the exact difference in the radar cross-section using finite difference time domain, but intuitively, if the shape is similar, you'll get very similar radar cross-section with a difference of maybe 1 or 2 dB, if I had to guess, maybe even less. So a key goal for my PhD was to then extend these plasma simulations to much larger computational domains using modern resources. I needed to stretch the domain in the trailward direction by about 4 times, if not more, and in the transverse direction by also 2 to 4 times. And I knew this would not be an easy task, but there are some tricks that I used. The first one is just taking better advantage of our computational resources, improving the parallelization of our code, and writing a whole new field solve algorithm that parallelizes the code better. And so what had been done in the past is that the subdomain boundaries, which is the boundaries between different regions simulated on different compute cores, initially the boundaries were parallel to the periodic boundaries, and they couldn't easily be changed to be the other direction by 90 degrees because the boundary conditions are different in that direction, which changes the calculations. And so I had to write a whole new subroutine, but doing so then basically it means if we stretch the domain in the trailward direction, then you can add as many subdomains as you want without them getting too thin, which messes up the computations in another way. And this prevents out-of-memory errors from crashing your code. And so my solver arranges the subdomains parallel to the open boundaries. That's trick number one. Trick number two is to relax the constraints on our discretization a little bit. This, of course, allows you to increase the domain size vastly in physical space. However, you have to make sure that you do so without introducing error in the computations. And so Glenn Sugar, in his work on the simulation of the meteor head echo, he very meticulously made sure that even the smallest length scale of this plasma, the Debye length, is resolved in his simulations everywhere. This is not a hard requirement. Ultimately, what it ensures is that all of the appropriate physics in your domain is being resolved of Debye shielding, where you have a charged particle and then the plasma will shield each particle. And so I have the color bar here set to turn red if the constraint is violated. It is not violated in the prior work, which is good. You want, your work to really be solid. But then I said, okay, if we increase the domain size, how much can we get away with it before, well, one of two things happens. One, the code blows up and then you get diverging electron density. That did not happen. So that's good. That's a start. But number two is that, yes, the constraint of the discretization in space being greater than the Debye length, it does occur, but only at a very tiny pinprick point, a singularity at the middle of the meteor head echo. And we're not trying to resolve the meteor head echo fully here. We are saying that we can make some level of approximation in the head echo, but we're trying to really touch upon trail formation in these larger simulations. Granted, both plasmas are very important, so we want to be very careful. And so I did a whole comparison of these results with one another, and they look very similar. And I will show you part of that comparison. I go into a little more rigor in my dissertation, but this is the domain with a head echo only. This is recreating the work of Glenn Sugar in 2019 very similarly, or also my work with the different ablation models. So this is very similar to that. And there's a region 1 meter cubed in this red box here. That same region now looks like this when we enlarge the domain. So beautiful result, really resolving both the meteor head echo and the trail. And it looks exactly the same in that red box. So results are the same. You've got the meteor head echo, you've got the meteor trail. You're seeing the meteor in so much more of a large picture, and what should it look like given the interactions between these particles with the atmosphere. So then I said, let's try different altitudes. Let's see how the meteor plasma varies as a function of altitude. So magnetic field is coming out of the page in these results. This is a cross-sectional plane perpendicular to the background magnetic field. And the atmosphere, again, is going from left to right. And this is the ion density. Ions are big and more mobile. And so this looks much more axisymmetric. Like you have a very trail, or the profile looks very traily. It looks very columnar at 95 kilometers, where the background atmosphere is much more dense and there's more collisional effects. At 105, not so much. It's a little more spread out. Electron density is not symmetric. Electron density is very interesting. And that's because the magnetic field is really breaking the symmetry when it comes to these very tiny and mobile electron particles that are going around at very high velocities in the domain. And if we then plot the electrostatic potential, which gives us an idea of what the electric field looks like in the plane perpendicular to the background magnetic field, what we find is that at 105 kilometers, the electric field just goes way crazier. It's much higher magnitude in this trail than it is at 95 kilometers. And the electric field vectors in this plane perpendicular point down the gradient of the electrostatic potential. And so we find that the electric field kind of pinches inward towards the points of higher electron density. Well, linear fluid theory predicts that Farley-Boonman gradient drift instabilities that cause turbulence onset in the plasma that causes non-specular trail echo observations that I mentioned earlier tend to occur above 95 kilometers when this condition is met, where you have the electric field vectors pointing up the direction of the gradient of the electron density. And this is exactly what's happening, especially at 105 kilometers, also at 100 kilometers, less so at 95, but still a little bit. That matches exactly with the experimental observations and the linear theory. And seeing trails mostly above 95 kilometers, but even more at 100 makes total sense from these results. One more result that I would like to show is that we quantified the meteor trail temperature for both the ions and electrons. They have different temperatures as you go downstream from like the meteor's position down in the direction of the trail. And what we found is that the ion temperature goes very high. This is because ions are initially ablated at like maybe 2000 Kelvin, but then they're moving at maybe 1000 meters per second. atmosphere is moving at 40,000 meters per second and scatters those ions like crazy. And then they develop, they're very heavy, but they develop wide velocity distribution functions that corresponds to very high temperatures, but then they cool down a little bit more quickly. And that's because the cross sections of their collisions increases as they slow down relative to the background atmosphere. Whereas for electrons, kind of the opposite thing happens. They don't go initially as hot. That's because they start out at 10,000 Kelvin. They're initialized at their ionization velocity and energy, but then their collisional cross sections tend to decrease as they go slower with respect to the background atmosphere. And so they cool down more slowly. And these results will inform existing particle and cell plasma simulations in the reference frame of the atmosphere, where those simulations, they don't have to resolve the meteor head echo. So they can have much looser discretization constraints that allows you to fully resolve the growth of instabilities, which we don't do here because basically the plasma leaves the domain due to the collisions before instabilities can develop, but you see that the right conditions are met. So that's kind of the point of these trail simulations that are larger than has ever been done before. So primary contributions of my PhD, of my work. First of all, we performed the first concurrent analysis of head echoes at 3 different facilities of the head echo population. I should clarify, these are not the same meteors, but it's 3 different geographic places on Earth. It's the same population of meteors coming from the space environment. Observed observation biases of each facility while eliminating other temporal biases, and then observing a very clear deceleration trend with more accurate decelerations being quantified using the Doppler shift. Then we invented a model to generate synthetic meteor head echo observations of meteors at any facility that you wish, and very rapidly then train neural networks to detect meteors at every facility. And then you can detect thousands of meteors instead of just hundreds quickly. Then we investigated the possible effect of non-isotropic ablation from a meteoroid particle using results informed by my collaboration with Joseph Ferguson, and then compared the difference using my particle and cell plasma simulations and determined the effect is probably very minimal. Then we performed the world's first computational plasma simulations that include both a meteor head and trail on a supercomputer, and then discussed how the results are pertinent to existing theoretical and computational results, and very beautifully resolved the difference in altitude. So kind of some ongoing work that I have in the pipeline and future work is that we would like to use scaled up meteor head echo simulations like I just showed you to inform radio wave scattering. So taking that big simulation, putting it into finite difference time domain. I've not done that yet with Alex Green, but that is the next step. I've done the smaller simulation domains and we've gotten some beautiful results. Fully automating detection of meteor head echoes at any facility. It's not quite fully automated yet. We've increased efficiency by an order of magnitude, but next step is, say, using an advanced neural network architecture that picks out all of the pixels where a meteor head echo streak is located, then fit a line to it, figure out all the complex data, and then that will reduce overhead to 0 with a few other techniques we have in the pipeline. We will further scale our particle and cell simulations. You did probably notice that the plasma gets close to the periodic boundaries, so there is some level of approximation there. So we can continue to use increasing computational power and parallelization techniques to increase the domain size and resolve more of the plasma and have it be more accurate. Also, maybe improving the boundary conditions, replacing the periodic boundaries could help with that. And then all of this will contribute to the ongoing search for interstellar meteoroids in these data sets. We think that some meteoroids come from outside the solar system. In fact, some have been observed, but there's a lot more need for quantifying the uncertainty in those observations and making those observations at facilities other than Altair, which I mentioned earlier. And we have all the techniques to do it. We just need to do it now. And so that's very much the next step that we are currently planning to do. I have published my work in my time here as a PhD student. Very grateful that my publications got accepted. We have 1 submitted that is currently in the pipeline and 2 conference papers at the National Radio Science Meeting. One of them took first place in the student paper competition, so I was very honored to receive that award. And I have also been very active in going to conferences and presenting my work via posters and presentations annually at the Coupling Energetics Dynamics of Atmospheric Regions Conference and American Geophysical Union, and also ERSI NRSM, as I mentioned before. Many, many people to thank. PhDs are standing on the shoulders of giants, many giants. First of all, I would just like to thank my committee so much for being here. Professor Sigrid Elschot, you have been just the most supportive advisor. I couldn't have asked for any better of a situation to study meteors entering Earth's atmosphere. Professor Meers Oppenheim, who is online, you've been a wonderfully supportive co-advisor. Dr. Nicolas Lee, he is not currently in the room, but he was very much also an advisor to my work, endlessly sourcing me ideas for my research, making sure I never ran out of ideas. And thank you very much to Professors Farhat and Hara for taking valuable time out of their day to be here today, and also for teaching just the most exceptional courses that I took at some point during my PhD, and teaching me techniques that have been very valuable, even if not directly applicable to this, through teaching me how to think about my work. And Professor Capelli, I know we have not interacted too much yet, but it's been very much my honor to have you here, and also serving as the dissertation committee chair, because as you all know, you need someone from outside of AeroAstro, and your research is in the perfect field. So yes, many more people to thank, but mostly I also want to recognize PhDs require funding. And so I received many grants from the National Science Foundation. So thank you very much to the NSF and to all of the awards. Also, 5 teaching assistantships from the Department of Aeronautics and Astronautics taught me wonderful teaching skills as well, which I'm very happy about. 3 years of fellowship from Stanford, so thank you very much to VPGE. Thank you very much to the lab. I don't have time to go through every person. Again, there's so many here, but we've had some wonderful times together, touring of radar facilities, hosting the Crown Prince and Minister of Luxembourg. Thank you very much to Dana for keeping the lab running in many ways, and all of you for being with me at conferences. And thank you very much to all of the people who graduated before me in SESS. They've been wonderful mentors and advisors, and also just student supporters, although they're no longer students. Thank you very much to my peers in Peru who interned with me and giving me moral support as I navigated a foreign country and speaking Spanish and all of those fun things, and also interning at a radio observatory where I collected some wonderful data. That was separate from the 2019 experiment, but that was fantastic data that we're analyzing. Thank you very much to these supporters in Peru. These people have been wonderfully, wonderfully supportive, and just kept things very positive as I did my research. Thank you to all of my friends these are friends specifically outside of Stanford. Many of you are here today or on the Zoom. I tried to find photos of everyone. I'm so sorry if I missed you, but consider yourself included in this set. And thank you very much to my Stanford friends, many of you who are also here, especially in person today. So these are all people I met at Stanford. Lauren, I went on runs with, so I've got the Strava there. We did not have a photo in person. And last but not least, thank you very much to my family, and one friend of family who is also in this photo, but then my mother and father and grandma, and then all of the other family members that are very relevant, as you can see in these photos. Don't forget there is a blood moon tonight. It's around 11 p.m. I'm hopeful that despite the fact that the forecast was cloudy, there were some breaks in the clouds. I did see the moon last night, so definitely look up around 11 p.m. or a little bit later than 11 p.m. Thank you. Any questions? I see a hand raising in the back.
Got one. When you you're generating your synthetic data,
Yes.
was there an aspect that was particularly was hard for your machine learning algorithm to deal with? Like, was the textual very hard? Were not the trails ignore?
That's a very interesting question. So the question, for those who might have not heard Michael, is that, is there any particular aspect of the synthetic head echo model that I developed that generates synthetic head echo observations that, if I understand your question correctly, is hard for it's hard for the neural network when it's being tested on real data and it's looking for real head echoes. Is there any feature in the real head echoes that is missed by the synthetic algorithm that then causes meteors to get missed. Do I understand your question?
Yeah, is there like some aspect that's like very difficult for your algorithm?
I would say yes. It is surprisingly good at detecting weird head echoes or head echoes that maybe don't have like the sync dependence in signal strength or something like that. The point is like neural networks tend to be pretty good at like doing something similar to what a human eye would do. In those weird head echoes, usually you have part that looks enough like the synthetic data that it'll still get detected. However, what I would say is the trickiest is at a facility like Millstone, where you have a beam at an angle, you get situations where you can have head echoes that appear to be going up in altitude, but really they're going up in range as they're descending, but cutting across the beam at a weird angle. The Doppler shift of those is in the wrong direction, and it's very hard to train the neural network with Doppler in both directions, because what happens is then you get Doppler of zero velocity as well. A lot of other phenomena have zero velocity, and that causes the false positive rate to go through the roof. And so I avoid training on any meteors that are going in the wrong direction along the beam. And so that will require some improvements to the algorithm to try to detect those head echoes going the wrong way. Another one is just, again, I mentioned very faint meteors. So that is just improving the neural network architecture, maybe applying this work to Felix Lee's prior work, which just is the most capable and accurate neural networks, would make a lot of sense. And so that's some of the work we currently have in the pipeline. I did see a question from Raymond.
So for your simulations, are you assuming with a single ion species? And if so, what species and how accurate of an assumption is that?
So Raymond is asking if in my particle and cell plasma simulations, I'm only simulating one species of ions. And yes, we are. And yes, this is an assumption that we are making. There's two assumptions embedded in here. Number one is that the meteor is only composed of one material. That is, we're using sodium as a representative material. But the answer is it's definitely future work to simulate meteors with multiple elements. This is called differential ablation in the field, where you have multiple elements in the meteor. They might be ablating at different rates, and also at different rates that change over the duration of the observation. And so that is something that I'm very excited to investigate further in the future. The second assumption is that there is also a background ionospheric plasma that exists in the ionosphere, and we are resolving that in our simulations. That tends to be nitrogen. And in the simulations, we're kind of just assuming that it's sodium. It's a little bit more massive, but ultimately the mass difference is not that great between N2 and sodium. And so ultimately, it really doesn't affect much. The collisional cross sections are kind of a big part of that assumption, but the problem is those collisional cross sections have such high uncertainties already. They're usually based upon experiments with order of magnitude uncertainty, approximately, depending. And so really you need a more accurate model for those cross sections to dive deeper. And we currently have a lab member that is touching on that with quantum mechanics. Ashwin, you have a question.
The very last result you showed, you explained that the initial temperature of the electrons is lower than the ions. I think you explained it, but I didn't understand why.
Absolutely. So Ashwin is asking, why is the initial temperature of the electrons lower than the initial temperature of the ions? So actually what's happening is that the ion temperature is starting out much lower than the electron temperature, but this is not being captured in these plots because they undergo their first collision with the background ionosphere, or background atmosphere, excuse me, so quickly that they heat up almost instantaneously. And the way I'm quantifying temperature here is very specific. I'm fitting a Gaussian function to the velocity distribution functions. And it's a bit of or I don't want to say it's quick and dirty, but it's one way to quantify temperature. The plasma distribution functions are not always Gaussian or Maxwellian, but it's a way of measuring the temperature that it's more accurate in the trail. And so we're really looking at the trail temperature dynamics here. But indeed, we definitely expect the ion temperature to go through the roof as soon as they start undergoing those collisions, just because of the velocity difference between ions and the background atmosphere. With electrons, they're initialized at the ionization energy, because like it takes a certain amount of energy to kick an electron out of the orbitals, but then that electron is going to have a temperature of about 10,000 Kelvin or on the order of, and then it's just going to retain that temperature because those electron particles are already, they're so light that they're already going so fast relative to the background atmosphere that further collisions don't affect the temperature or drive it up that much.
I think the bear had his hand up.
Can anyone translate bear?
Barry wanted to let you know that Barry's gonna miss you.
Aw, I will miss Barry too. He's been a very important presence in the lab. Dan Hedges has a question.
So, for the facilities where you use your machine learning to extract, data, are they using that now? Are other people already using it?
Ooh, this very good question. This touches on something. And so the question is, are the facilities that I've been collecting data at, are they using the machine learning algorithm that I have developed? In order to do so, you need a machine learning algorithm that operates at real time or faster, ideally quite a bit faster than real time. What does that mean? That means as you're collecting radar data, like every second on those plots that I showed, you need a machine learning algorithm that is faster at identifying meteors in that data than the data is coming in at. And that will require generally pretty good or pretty modern computational resources. And that is a very hard thing to set up at these facilities. So currently the goal is just to make the algorithms faster and faster and more appropriate for that real-time data collection. Once we get above real time, then we can start thinking about implementing those algorithms to their tool chains and their signal processing chains, specifically for meteor experiments. They do for other types of experiments like incoherent scatter radar, which is just looking at plasmas in the ionosphere and not meteors. They don't necessarily use machine learning, but they do have other algorithms running in real time.